Good morning. So, last class we looked into different atomic orbitals, right? We know that we have 4 different types of orbitals, S, P, D and F, right? And how many sublevels each of them have? How many sublevels S has? Okay, so how many S has? 1. P has? 3. Odd numbers, right? And D has 5 and F has 7. Okay. And we know that the energy also increase in that order. S is the lowest, F is the highest. Now, we looked at electronic diagrams also. Each sublevel can hold how many electrons? 2 electrons. Each of those boxes had 2 electrons, and remember we put them as up and down arrows. Okay. So we will do more practice on writing electronic configurations in this class. This is just before that we are getting into that mood. So consider some of the alkali metals. The first lithium, sodium, potassium, rubidium, and we have the electronic configurations given here. Can you see a pattern? What is it you notice? How they are all ending? With an S1 configuration? Every one of them have S1 at the end, right? Okay. Consider the alkaline earth metals, group 2 metals. How are they ending? Halogens, fluorine, chlorine, bromine. How are they ending? Okay. And some of the noble gases. They are all ending with a P6? Okay. Now, we have seen the periodic table. We know the groups, and so far we knew metals, non-metals, transition metals, inner transition metals. We are going to see another type of classification also in the periodic table. The first 2 groups, group 1A and 2A, are called S block elements because their electronic configuration, when you write, they will always end with, the first group will end with S1, the second group will end with S2. So those 2 groups are called S block. Now if you go all the way to the other side, the 3A onwards up to 8A, if you look at their electronic configurations, they would always end with P. 3 will be starting at P1, then P2, P3, P4, P5 and P6. There are 3 sublevels in P, right? Each sublevel can take 2 electrons. So total a P orbital can take how many electrons? 6 electrons, right? And there are 6 groups in there in P block. So that area is called the P block. Now the transition metals, you have at that in between part, that is called D block, because when you do the electronic configuration you see that they will have D orbitals also getting filled. Okay. Now if you count the number of columns there, how many columns are we counting in D block? 10? Okay. Does it make sense? How many total electrons D block can have? 10, because it has 5 sublevel. Each sublevel is taking 2, so total 10 electrons. Similarly, come down to the inner transition metals. Those 2 periods which we see in the bottom of the periodic table, which is given separate. How many are you counting? Or before you count, can you predict how many will be there? 14 because F has 7 sublevels and each sublevel can take 2 electrons. Therefore, there should be 14 of those groups. So, this is another way of classifying the periodic table, and you need to remember this position because this is going to be important in writing electronic configuration. If you remember this, you can write the electronic configuration of any element. You don't need those orbital diagrams, the boxes, all that stuff. Okay? We are going to practice on that. So, as it says, notice that the number of columns in SPD and F blocks is the same as number of electrons allowed in each sublevel. That's what we just counted, right? S can have only 2 electrons, so there are 2 groups, S1 and S2, group 1 and group 2. Then P can have 6 electrons, so there are 6 P groups, and D can have 10 and F can have 14. So this allows us to use the periodic table to write the electronic configuration without the aid of an orbital diagram, as I just said. Otherwise, imagine if you want to write the electronic configuration of like gold, which is atomic number 79, how many boxes you have to draw, right? That is not feasible all the time. So we need something easy. We can just, because remember, anything we do, you will go back to periodic table, right? Periodic table determines the entire world of chemistry. So we will come back to periodic table, and using that we can write the electronic configuration of anything. So here are certain things you need to remember when you write the electronic configuration. The principal energy level number, that number which we write below the orbital symbol, like when we saw the electronic configuration, we saw like 1s2, 2s2, 3s2, like that, right? So that number which comes below before the symbol, that is the principal energy level, that will be the same as the period number in the periodic table for S and P blocks. Okay, that is an important point. Remember that. For S and P blocks, the period number is the same as the number which you write before S and P. Okay, so we have periods starting 1, 2, 3, 4, 5, 6, 7. There are 7 periods on the periodic table. So for each period, S and P has the same number as the period number. For the D levels, the principal energy level is going to be, are you okay?
Yeah, I forgot my inhaler.
Goodness.
I really should have it.
Okay, if you have it in the car or something, please do get it. So, take care, okay? Can't even speak. So for the D sublevel, the principal energy level is 1 less than the period number. That means, we will see when we do an example, what do I mean by that. So when we come to 4th period, that is where you will see first the D level starts, but it won't be 4D, it will be 3D. That's what it means. Whatever the period number, minus 1 will give you the number which comes before D. For F, it will be period number minus 2. So when you come to 6th period, that is when you encounter the F level first, but that will be 4F. Okay, 6 minus 2, 4F. This is what I mean by that. Look at this. So here is the period number on the left side. Each of the rows are called a period, right? We know that. So the first period, we start at the left side, first period. Which element will be this? 1s, hydrogen, and then we have nothing else on the first period except helium. So helium is also 1s. Then we come to second period. We are starting here at 2s. Nothing else in between. We come to P block, that is 2P. Now you come to third period, it is 3s. Again nothing else, only P block, so 3P. Come to fourth period, you have 4s in the periodic table, 4s is the potassium and calcium, and once you cross 4s, you encounter the first row of transition metals, which is the D block. But remember the number of that D block. Is it 4D? It is not, it is 3D. That's what I mean by the D, the number which comes before D is 1 less than the period number. So this is in the 4th period. So 1 less than 4 is 3. Similarly, if you look at the 5th period, 5s, and when it comes to D, it is 4D. 5 minus 1, 4D. But P and S is the same as the period number. 4s, 4p, 5s, 5p, but D will be 1 less. Now, the inner transition metals, the F block, you all know that their position in the periodic table is actually here. This gap you see here, right? That is where they have to be positioned. But if you position them there, our periodic table will be too stretched. That is why we just write them below. But this is what it means. This gap, that is why you look at these arrows, how it is given. This entire thing you see in the bottom should be fitting into this gap. Okay? So this is the expanded part of that. So when you come up, if you go in this way from left to right, 6s, 5d1, and then you have the F block starting, and notice the number of the F on the 6th period. So this is the period number given here again. 6th period, what is the number of F? 4. How do we get that? As I said, for F, remember, whatever is the period number, minus 2. So again, the next period, 7th period, when it comes to the F block, it is only 5F. So we go from left to right on the periodic table. We start from the leftmost corner, go all the way to right, then the next period, then the next period. We keep moving until whatever element we are looking for, until we reach that position. Okay? So we will do practice on this so that you will all be able to do this. So let's say our goal is to write the electronic configuration of phosphorus. Your first goal is locate where phosphorus is on the periodic table. Remember, you have a real periodic table. You are not having this, periodic table which is empty, right? You have a real periodic table and you have to now memorize the locations of these blocks. The first two groups, S block, the main group, the rest of the 6 groups, those are P block, transition metals in between, D block, and the bottom 2 are F block. Those are the only 4 sections. So you locate phosphorus first, and you locate phosphorus below nitrogen if you look at the periodic table with atomic number 15. So starting from the leftmost corner, you have to go all the way to 15. So here, just for the ease of showing, they have moved helium also here. Remember, in the first period you have only hydrogen and helium, correct? Okay, so first period, S1, S2. When you reach helium, you have reached 1s2, correct? So you don't have to write 1s1, 1s2. When you finish a particular type of orbital, you can just write the last one. Okay, so say for example, if you are going to write here, you will write 1s2 when you are at this point. Now you come to second period because there is nothing else on the first period, right? So you come to the second period starting at lithium, 2s1. On beryllium you are at 2s2, right? But we have to go all the way to phosphorus. So whenever we finish an orbital, we write it down. So we write 2s2. Nothing else in the between. We are all the way coming to boron, which is the P block. Second period P block. What is the number? 2p, because it's a second period. Remember, for S and P, it's the same number of the period. So 2p. And we are going all the way here because we need to keep going, right? When we reach here, what will be your number? 2p. So P1, P2, P3, P4, P5, P6. So you will write 2P6. Well, we have to go to the next period now. See, our goal is to reach until phosphorus. When we come to the next period, it is period number 3. Sodium and magnesium. When we cross up to here, where are we? Where are we standing? 3s2. So you will write 3s2. Are we done yet? No, we have to go all the way to phosphorus. So we are starting right here, standing at the beginning of aluminum, which is 3p1, 3p2. We are on phosphorus. What is our number? 3p3. So you will write, you need to go only up to phosphorus, right? So that is your last one, 3p3. So that is the electronic configuration of phosphorus. Okay, so just looking at the periodic table, all you need to do is go from left to right, finishing everything. And on the periodic table, all you need to remember is the first two groups, S1 and S2. You know that S has only one sublevel, it can take only 2 electrons. So only 2 groups come under that. P has 3 sublevels, it can take 6 electrons, so those 6 groups come under P. D has 5 sublevels, it can take 10 electrons, the transition metals are under D. Bottom again, F block, which can take 14, and on the F block there are 14 groups. So you keep going from left to right, top to bottom until you reach what you need to. And keep remembering, S and P has the same number as the period number. Whichever period you are, it's the same number. For D, it is period number -1. For F, it is period number -2. That's all you need to remember. Let's do another example. Let's do the electronic configuration of manganese. Everyone look at the periodic table and find out where manganese is. Manganese is, what is the atomic number? 25. Everyone located it? Okay, so here in the periodic table also it is highlighted. So we are again starting with the leftmost corner and going from left to right. So the first period, only 2 elements. When we cross that, what do we get? 1s2. Come to the second period. First 2 elements, lithium, beryllium, what do we get? 2s2. On the second period, do we have anything else? We have the P block, right? Keep going from left to right, second period, until after you finish everything on one period, then only you can come down to the next period. We are going from left to right fashion. Okay, so in the second period, what else is left? The P block, and we have to cross all that, right? Our goal is to reach until manganese. So when we cross the P block in the second period, what do we write? 2P6, because we have crossed all. We can just count each group. When you cross each box, you can count. Okay, come to third period. First 2 groups are 3s2. What else is there on the third period? The 3p block. Are we crossing all 3p? Yes, we are, right? Because manganese is even after that. So we are crossing all that. So 3p6. Come to fourth period. Potassium and calcium. When we cross calcium, where are we standing? 4s2. So we are entering the transition block, which is the D block. So what D it is? It is the 3D. Remember, on the fourth period, the D block, it is 4 minus 1, right? So it is the 3D we are entering, and you see manganese is in that row, correct? So start with the first D onwards count. Sc, scandium 21, that is D1, titanium D2, vanadium D3, chromium D4, manganese D5. So what do we write? 3D5. That is your electronic configuration of manganese. So if you remember that, guys, just left to right, keep going until you reach what you are looking for. Keep in mind S and P same as period number, D period number -1, F period number -2. That's all you need to remember to write the electronic configuration. Has everyone understood this? So yes, manganese has 25 electrons because it is the atomic number 25. So as it says, start at the top left corner of the periodic table, move from left to right, top to bottom until we reach manganese. And keep writing. That is the only way. There is no other magic formula here. And you have the periodic table always with you. Okay, let's do more practice. We are going to write the electronic configuration of aluminum now. Locate aluminum. Where is aluminum? Everyone see aluminum? Okay, keep going. Start from the leftmost corner. When we finish each orbital, write it down. Start. Start, guys. Okay, 1s2. What next? 2s2. So you all know this. You are just being lazy, right? And I am thinking that you all don't know this, so I am waiting for you to write. Okay, all right. Then some miscommunication there. Okay, 1s2, 2s2 and 2p6, 3s2, 3p6. Where is aluminum? Right there on 3p1. Okay, you go ahead and write the rest of them. I'll keep quiet. On the book or on the thing? What do you mean? Write it down here. It's just practice. It's not a clicker question. That's what you mean? How can you write on the board? I can only write on the board. No, write it on your book. It's for you to learn. I know how to write them. Don't worry. So you go ahead and write it on your book and we'll check. Leave the last one alone, probably mercury. I mean, if anyone wants to try, go ahead. I might show you mercury again because that has a lot of other things also. I mean, comes to F block also. So. What is it, Thomas? Ask me.
If it's only using one of the elements, like if it was only to hydrogen,
Mm-hmm.
would it just be 1s or would it be 1s?
1s1.
Okay, thank you.
Are we making progress or is still everyone is on second or? No, right? I'm writing down so that you can check your answer. The first two right? Everyone is good? Okay, wonderful. How about bromine? Is there any question on bromine? Yes. Why? It is on the fourth period. And for D, what did we say? Period number -1. So that is 3D. Right? S and P has the same period number. D is period number -1. F is period number -2. So bromine is on fourth period. Okay, let's do zinc. Where is zinc? Fourth period, just before gallium, 3D10. Guys, if anyone has any questions on this, please do ask me, okay? It's not a test. I mean, I just wanted you guys to try on your own, but anything you are not getting asked what I am writing, please feel free to ask.
You said leave the last one?
Yes, last one I'm going to do that one. But so far is everyone good? Up to sync? No confusions whatsoever? Okay, let's write mercury together. Everyone located mercury? Mercury is number 80. Okay? Sixth period. So, okay, up to sixth period, S2, when I'm crossing cesium and what is that, strontium, barium, right? Barium 56, that is where right now I am at 6s2. Now 57, lanthanum is 5d1, correct? Now remember, your gap comes right there. The F block starts right there, right? So we are jumping from 5D to the F block. What F block are we going? 4F. What is the number comes before F block? Period number minus 2. Which period are we in now? 6th period. So for 6th period, 6 minus 2, 4F. That's where we are starting now. In 4F, are we crossing all of them? Okay, let me go to the periodic table. So this is what I just said. At 57, 5D1, lanthanum. Now this group comes, see, 58 onwards up to 71 should be fitting in here. Because if you look at the atomic number, after 57 you see 72, right? So there is that 14 gap which comes from 58 onwards 71 right here. So 5D1, then you are jumping to 58 which is 4F1, right? So when we go from 58 to 71, what did you finish? 4F14. Mercury is 80. We have to go up to 80, right? So after 4F14, which is 71, you are back to 72, which is 5D2. D2, D3, D4, D5, D6, D7, D8, D9. Mercury is D10, 5D10. We will stop right there because that's what we were looking for. Now, you had 5D1, then 4F14, but Mercury is 5D10. When you write 5D10, that means that 5D1 is also included in there, so you don't have to show that separately. You can just remove that 5D1 and write 5D10 once for all. Yes? F has to come before the D. We will go in that order only because that determines the energy level also. Remember, the lowest energy gets filled first, right? 4F is lower in energy than 5D. So if we proceed with this, this is the correct order of filling, that is 5D1, 4F14, and then rest of all the 5D. So we have up to 5D10, but then we will cross this out, or you can just eliminate that, because 5D10 means 5D1 is already included in that, right? So there it is. If you look at the electronic configuration so far, I mean up to zinc we didn't have a problem. Look at the Mercury as we just wrote, 6s2, and then comes 4f14, and then 5d10. In your exam, I don't think I'll be asking you to write anything on the F block, okay? But you need to know, but I'm not going to ask you anything to write on F block. You will have only stuff from other parts of the periodic table. Yes? Yes, that's what I'm saying. You don't have to write the 5D1. You can just proceed whatever is the last one is. 5D11, D cannot have more than 10, so D11 is invalid. Count up to 79, which will be 5D9. Because in the periodic table, if you count how many D columns you have counted for reaching up to 79. 1, 2, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 columns.
I think what they're asking is if it ends in the F table, like say it ends on EY or something, would you put 5E1 and then end it with 4F?
Oh, okay, you mean, let's say for example, you want to write the electronic configuration. Let us say, let us pick up something, Europium, EU, 63. Let's say you want to write that. That's what the question is? Okay, then it will be 5D1, 4, F1, F2, F3, F4, F5, F6. Now, that is how you write the electronic configuration. Why I am not going to give you these questions is, when it comes to this F block and D block, they are very close in energy, and then there is something called half-filled and fully filled orbitals, which you are not learning, okay? You are just learning very basics of the atomic orbitals. So that time they will migrate, the D block will migrate to F block and you might get a different configuration. That is why I'm not going to ask you to write something in F block, okay? Because it's beyond your syllabus or it's beyond the scope of this class. So when it comes to that level, there is a lot of other things also come into the picture. So you don't worry about them, you just know this is the order we go. I won't be asking you to write anything in F block. Justified? Okay. Now let's do a clicker time. Calculator? No, that wouldn't work. That is true. Okay, it's good. It's a very easy one. Just you know how to do this. So I want 100%. It's asking for the electronic configuration of silicon. Locate silicon on the periodic table and then write it and pick up only the correct one. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay. Everyone has clickers? Okay. Oh, there it is, 21. Okay. Which one is it? C? That is correct. So, let us see. Uh-oh. I still have a couple of them wrong. What went wrong? B is 3p6. Silicon is in the 3p block, but when you cross two groups, you are right there, right? 3p6 means you are going all the way to argon. Way too many electrons. Remember, when you write the electronic configuration, this total number you write, that represents the number of electrons. They should also add up to the total number of electrons in an atom. You cannot go more than that, right? When you say 3p6, you are in argon. Now, what happened to D? D is, well, the total number is right, but look at the P. P8. Is that allowed? P cannot have more than 6 electrons. So, it is not allowed. So, C is the correct answer. Okay, so we just wrote electronic configurations, which is called long version. Remember when we wrote mercury, we had to write a big, huge line, right? So when we work with electronic configuration, we use an abbreviated form, which is well, let's just learn the abbreviated electronic configuration, which is often used with many electrons. Say if it is something like silicon or up to third period, you are good. You have only S and P, you can write it. But when it comes to more than that, instead of writing the entire thing, we use an abbreviated version. So look at the electronic configuration of iron, Fe, and argon. If you look at the electronic configuration, up to 3p6, they are exactly the same, right? Argon is 18, iron is 26. So up to that 18 electrons, they are exactly the same. But since iron has 26, we are again after 18, we are moving for 4s2 and 3d6 up to reach iron. So we can use the symbol of argon given in square brackets to represent argon's electronic configuration. So for iron, instead of writing all that up to argon, which is exactly the same, we will put argon in place, and whatever is after that we will write 4s2 3d6. Now one thing to notice is only noble gases are used for abbreviated electronic configurations. Okay, only noble gases. So what you do is, if you want to write an electronic configuration of something, find the noble gas just before it. Put the noble gas in square brackets and then start with the next period and write the electronic configuration only for that last period. So for iron, if you were looking in the periodic table, the noble gas before iron is argon, which you will put in square brackets. Then you are checking, iron is in the fourth period, so fourth period starts with 4s2, then comes 3d, iron is in that row, so you go all the way to iron, which is 3d1, 3d2, 3d3, 3d4, 3d5, 3d6. So you just write argon in square brackets and then 4s2, 3d6. This is called the abbreviated electronic configuration. Let's practice some more. Let's write the abbreviated configuration for aluminum. Which is the noble gas before aluminum? Neon. So we can put neon in square brackets. So we write neon. Then we look for which period. After neon, whatever it is, we have to write it down. So neon number 10, that was up to 2p6. Aluminum is in third period, so we have to write everything on the third period. Third period starts with what? 3s2, and aluminum is where? 3, oh, sorry. Aluminum is 3p1. So this is the abbreviated configuration for aluminum. Let's do for scandium. Which is the noble gas before scandium? Scandium is number 21. Argon. So we can put argon, Ar in square brackets. Now scandium is in the fourth period. So fourth period starts with 4s2, and for scandium after 4s2, remember it is the D block, and which number D? 3D, and scandium is the first one, so 3D1. Okay, next one, potassium. What is the noble gas before potassium? Again argon, so we put Ar, and potassium is in which period? 4s. It is the first one in the S1, right? Sorry, S block, right? So it is 4s1. Okay, bromine. Which is the noble gas before bromine? Argon again. So we put argon. It is too easy to make that mistake. Looking at krypton, which is after bromine. Please remember, it is the noble gas before the element you are looking at. Okay? However far away it is. The noble gas before, that's what you are looking for. So argon is before, okay. Now we comes to bromine, which is in which period? Fourth period. Okay, so fourth period starts with 4s. We have to go all the way to bromine now, just like we were doing previously. 4s2, 3d10, then comes 4p, bromine is in the fifth column, right? So 4p5. Zinc, which noble gas before zinc? Again argon. Zinc is in which period? Fourth, starts with 4s2, 3d10. So these are the abbreviated electronic configurations. So find the noble gas before it, and then whatever is wherever the element is existing in that period you have to write everything. So you are writing only the last period configurations. Okay? Before that everything you are showing that as the noble gas in square brackets. Okay, let's test this also. Here it is. What is the abbreviated configuration for chlorine? Pay attention, okay? We'll stop at 2. Come on, I need one more answer. I don't know what is taking so much time. All right. You lost the chance. What is it? Okay. Now the next topic is valence electrons for the main group elements. Have we heard this word before? Valence electrons? In the lab, right? The same thing. So the last filled principal energy level is called the valence level or valence shell. So the valence level contains electrons that are in the highest in the energy and occupy orbitals that extends farther away from the nucleus. And those electrons are only participating in bonding. That is what when we were doing the Lewis structures, we were calculating how many valence electrons are there and how they are arranged and all that, right? So they are the electrons basically determines the bonding, how the arrangement of atoms are in a molecule, all that stuff. So valence electrons again occupy the orbitals in the valence level, which is the outermost principal energy level, and all other electrons are called core electrons or inner electrons. Inner electrons pretty much don't do anything in an atom. They just stay inside. That's all. The valence electron, which are on the outer shell of the atom, they are responsible for almost all matters we see with the atom's behavior. They are responsible for everything, the valence electrons. Now, how many valence electrons are in bromine? I said the last filled orbital, last filled principal energy level. How many electrons are there in the last filled level? Last filled level is number 4. How many? You see a 4s2 here and 4p5. 4 is the last filled level. So how many total in that level? 7. Now there is another way of calculating this without even looking at the electronic configuration, the way we did in lab. What is it? Does anyone remember? The group number. The group number is the same as the number of valence electrons. Yes, right. So bromine is in group 7, right? So it is the same as that. So here valence electrons which are on 4p and 4s, because that is the last filled principal energy level. Now as it says, elements in the same group have same number of valence electrons. So go fast. Fluorine, lithium, sodium, carbon. Which group is carbon? Silicon, Pb, lead. Which group is Pb? 4, same group as carbon, right? So the valence number of electrons, okay? You don't have to worry about anything, just check in which group they are, that's all. You know this, guys, you did the lab and you did all calculations for so many of them, right? So it's the same as the group number, the valence number of electrons. Okay, little more practice. Magnesium. Magnesium is, yes, magnesium is 2. Sorry, I blocked out for a second. Carbon, boron, chlorine, selenium.
6.
Okay, good. There it is. Which group they are and that many. So now we are going to look into electronic configuration of ions. So far we were writing the electronic configurations of neutral atoms, right? Now for ions, what is different from atoms? Their number of electrons is not the same as number of protons, right? When the number of electrons and protons are the same, they are neutral. But for ions, either you have more number of electrons than protons, or you have less number of electrons than proton, right? Atoms gain or lose electrons, that is how they create ions. So what are anions? Negatively charged ions. How an ion will be negatively charged? It has extra electrons, right? When electrons are negatively charged, so if it has extra electrons, it will be negatively charged. So what is positively charged ions called? Cations. And how do we get positively charged ions? Loose electrons or less number of electrons, right? Okay. So say for example, bad slide, answer is given right there. So what is the point? Anyway, write the electronic configuration of sodium plus, that is our goal. So what you do is, this is, let's read again. So this is your thought process. First you locate sodium in the periodic table and you see that sodium's atomic number is 11. right? The neutral sodium has 11 protons and 11 electrons. But Na plus means it is showing an extra positive charge. What does that mean? It has one less electron. So how many electrons sodium has? 10 electrons, right? So you just have to write the electronic configuration until you get 10 total number of electrons. So 1s2, 2s2, 4, you need 6 more for 10. So when you write 2p6, you are showing 10 electrons, right? So the electronic configuration of Na plus is 1s2, 2s2, 2p6. Remember, electronic configuration, we are showing the number of electrons. So if it has only 10, you can show only 10, right? That is the deal. So let's practice on electronic configuration of some of the ions. Br minus means what? How many electrons Br has? 35. Br minus means how many electrons? 30. Yes, Cassidy. Doesn't matter. We are looking into that. I mean, later you will see why these ions form the particular, why always group 1 form 1 plus ion. We will see to that. Okay? They want to have a special kind of uniform configuration. We are going into that, developing the story. So, Br minus has total how many electrons? 36. So, if you write the electronic configuration, what would you write? Let's go ahead and write. What does it say? Oh, it says long and abbreviated. Okay. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. If it was neutral bromine, you will stop at 4p5, but you have one more electron. So where can you stop? 4p? Why? One more electron. So one after that, right? Neutral bromine 4p5, but you have to go for one more because Br minus has 36. Yes.
When you do that, you're showing that it's
Yeah.
all that's been shown. You wouldn't actually call that out, essentially, your KR, right?
Well, the question says in long and abbreviated, so I was writing the long first.
And look, I just get confused by where we end up with KR, we're adding electrons or something.
We are not ending up with Kr. It's not just Kr, it is in the square bracket.
Means if you're following the periodic table, that's kind of what I was just asking. If you're following the periodic table and you use that configuration, it shows that you're at KR.
Yes.
How do you differentiate between the two? Does it matter that they have the same configuration?
The configuration means what? Electronic configuration. They both have the same electronic configuration. That's all it means. Krypton is different, bromine is different. But their electronic configurations, when it is Br minus, it is the same as kryptons. Okay? Their nucleus is different. Nothing changes in the nucleus. Right? So, number of protons, the social security number remains the same. Only the number of electrons change. Okay? So, it's still two different species. We are just electronic configuration means we are looking only at the number of electrons. So, this is Br minus 4p6, which is the same as what? But remember, when you do this is how you differentiate. You just can't write Kr. You have to put that at square bracket just to say that only number of electrons are the same. It's not Kr. See the difference? Oh, Ar, not K. Well, no, bromine, after bromine it is Kr. With that many electrons, that's what you are writing.
So the
Yes, that is the abbreviated one. Now let's do for N3 minus. Nitrogen is number 7. 3 minus means how many electrons? 10 electrons. So we have to go all the way up to 10 electrons. So 1s2, 2s2, you have 4, 2p6, which is the same as what? Which is the same as neon. So the abbreviated one will be Ne in parenthesis. Yes.
Is it always, are they always going to end on a noble gas?
That is the thing. Why do they form ions? Why do we call it noble gas? Everyone else wants to be like noble gas. So they tend to gain or lose electrons in order to have the same number of electrons as the noble gas. That is their goal. That is why other elements form ions and noble gases do not. Because they are happy by themselves. They are noble. Everyone else wants to be like them. Okay? So that is, it's only the number of electrons they can have. So they do that. Rest of the things they cannot have the same as the noble gases. Okay, K plus. How many electrons in neutral K? 19. K plus means 1 less electron, 18. So we write 1s2, 2s2, 2p6, 3s2, 3p6, which is the same as Ar. Sr2 plus, strontium after rubidium, which is number 38. So we are writing, well, 38 is the neutral Sr, 2 plus means how many? 36. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Do I have to go for any further? 36 electrons. Which one is it? What is the electronic configuration? Which noble gas has this electronic configuration?
So the abbreviated version is actually just the symbol that has the same configuration.
Yes. It's not the same element. That is why you can't just write Kr. Kr has to be in the square brackets.
But you don't need the rest of the...
No, abbreviated version means only you need that. You don't need the rest of it. But since this question is asking us to write long and abbreviated, that's what we are doing. S2 minus. S is number 16. 2 minus means how many electrons? 18. So we need to show total 18 electrons. 1s2, 2s2, 4, 2p6, 10, 3s2, 12, 3p6, 18. What is the element for this configuration? So after we wrote the electronic configuration of several ions, we see that they are all ending up with some electronic configuration of some noble gases, right? So this is the goal. As I just said, all ions are formed because they want to be like the nearby noble gas. Remember when we talked about in chapter 2 why certain groups form always certain charged ions? We said for group 1 they want to be like the nearby noble gas. For them it is easy to lose that one electron and become like the previous noble gas. Group 2, it's easy for them to lose 2 electrons and become like the noble gas. That is why we don't see anything in group 4. Remember I said group 4 is right in the middle. Either they can gain 4 electrons or they can lose 4 electrons. That is why we don't see anything about group 4, what charge they form. Right? So up to group 3, up to aluminum, that boron, aluminum, up to group 3, it's easy for them to lose rather than gaining 5. See, noble gases, all of them have 8 electrons in their valence shell. Okay, and from nitrogen onwards, from group 5 onwards, it's easy for them to gain electrons to become like the nearby noble gas. So that pattern we have seen before, why they form always this particular charge, it is explained based on the electronic configuration. Every other guys in the periodic table wants to be like the noble gas in their electronic arrangement. So they form ions accordingly. Okay? So, electronic configurations, as I said, they are related to the following main, I mean there are so many properties which are related to electronic configuration, but these are the three main properties we will look at. That is relative reactivity and then something called ionization energy. Ionization energy is the tendency to lose electrons, especially the positive ions. Why do they lose electrons? That's what we will look into. And then atomic radii or atomic size, simply. So we will look into one by one. So reactivity, we have seen this chemical reactivity table, right? For the single displacement reactions, we have seen this table, and we know that the elements on the top are the most reactive. Look at the elements on the top, which group they belong to? Group 2, 1 or 2, right? Potassium, sodium, they both are group 1, barium, strontium, calcium, those are group 2, right? So the most reactive elements are of group 1 and 2. We can see that from the reactivity series. So the more reactive means what in terms of number of electrons? More reactive means easy for them to lose the electrons. Okay? If somebody can lose electrons very easily, more reactive it is. If somebody cannot lose electrons easily, less reactive it is. That was just stretching, right? Okay, looks like that. So, alkali metals, we know that the group 1 metals, alkali metals form 1 plus ion because they all have 1 valence electron. So, they just lose that 1 valence electron and form 1 plus ion. So, if you look at the oxides, the formula will be oxide usually what charge? Oxide is -2, right? So, you need two group 1 element for every oxygen. That is how the charge is balanced. What happened, guys? This is okay. The alkaline earth metals always form 2 plus ions. We know that. So when you write the formulas for oxides, 1 1 each, right? Because 2 plus and 2 minus, they are electrically balanced. Now, if you look at the properties of group 1 elements, let's say group 1 metals reacting with water. The first group 1 metal, lithium, if you put that into water, it kind of moves around but not doing much. You might see some bubbles coming out. But if you put sodium, yeah, you see something funny. The sodium is going to zoom move around in water and produces some smoke. Okay, potassium, fireworks, it reacts violently with water, creating a flame which has, you can see the flame there. Rubidium, it is almost like an explosion, that reaction. Cesium, you can see like a bomb, it even, that container which you held water, that is even exploded with that force. That container is broken. So, what do we assume from this? The group 1 elements, as we move down in the group, their reactivity is increasing, right? It is all water, only the elements are changing. So, when you go from lithium to cesium, just by looking at these pictures, you can say the reactivity is increasing down the group, right? As we go down the group. Yeah, if it is, that is why, many times people ask me, can we put some potassium in water? I'm like, no, we are not doing that here. I'm sorry. And I guess it's one of the very favorite high school chemistry experiments the teacher shows, putting a piece of sodium in water. That's all they go for. I don't think anyone goes for potassium, which is a bit dangerous. Sodium is okay, it doesn't burn, it just walk around and, you know, not walk around, run around in water and produce a lot of gas, and, you know, that's all. So that's fun, but potassium onwards it starts burning on top of water. So you don't want that. So reactivity, as we go down the group, for metals it's usually increasing. Okay, that's what we just see, one property. Now that second thing called ionization energy, the definition of ionization energy. Ionization energy is a measure of energy required to remove a valence electron from a gaseous atom. That is the definition. How much energy you need to remove one electron from the gaseous atom. So say for example magnesium gas, if you take the magnesium metal and, you know, change that into the gaseous form, if you want to remove one electron and make the Mg plus ion, you need to provide 738 kilojoules per mole of energy. That is a huge amount of energy. Okay, so in general, atoms with low ionization energy do not bind their electrons very tightly and are therefore very reactive. Well, you can think of this way. Let's say this is the magnesium atom, my hand. If I am holding on to my electrons very tightly, and Ashton comes here and she is trying to pulling away this electron. If I am holding on to this very tight, she has to use more force, right? That means, remember that force she is using, that is the ionization energy. How much energy you need to remove or pull away an electron from the atom. But if I am holding this chalk like this, just at the tip of my finger, not very strong, she can just come and snatch it away easily, right? Or she doesn't need to put much effort, she doesn't need to provide much energy. So low ionization energy, electrons are removed easily. Okay, that's what it means. So atoms who binds to their electrons very strong, if an atom is holding on to the electrons very strong, you need to provide more energy or less energy to remove the electron? More energy, or in other words, the ionization energy will be high or low? High. But if an atom is binding to the electrons very light, then you need to provide only less energy to remove it, or the ionization energy will be low. Good. Now if you look at the periodic table, what is the trend? What is the trend in ionization energy? What we see is ionization energy increase up a group or decrease down the group. They are one and the same, right? If energy increasing up the group or decreasing down the group, they are one and the same? Opposites? Okay. So ionization energy increases up the group because valence electrons becomes increasingly closer to the nucleus. We know that if you look at group 1 from lithium to cesium, as we go down, we are increasing the number of electrons and the size of the atom is going to get bigger, right? That means electrons are, size of the atom getting bigger means electrons are far away from the nucleus. So the nucleus is the attractive force for electrons. All the protons are inside the nucleus. So if electrons are far away from the nucleus, that force of attraction is also weak. Therefore you can remove them easily. Low ionization energy. Yes.
That's what I don't understand about this. The outer electrons are supposed to have more energy, but they're easier to take away.
Because the outer electrons and the valence electrons, they determine how an atom forms an ion. So they are in a higher energy level, right? That's what, okay, let's go back. So outer shell means the energy of the shell is increasing.
Right.
And the electrons on the outer shell is at a higher energy level,
Yes.
right? So it is easy to remove them. You don't need to give much energy because they are already excited. The shell has higher energy, not the electrons have higher energy. Don't confuse there. It is less binding, that is why the shell is at a higher energy. If the nucleus is really holding them tight, then they can't do much. They cannot move around. Okay. Shoot the next question. Still trying to digest?
When you say higher energy,
Yes. It's more. No, because the nucleus, the distance is very less, so the nucleus is holding them tight.
Why does the shell have a higher energy than the electron? What does that mean?
Well, electron, whether it is inside or outside, that is just -1 charge. It's the same. But where the position matters. If inside it is tightly packed, tightly closer to the nucleus, cannot move around, which is a low energy state, whereas outside, as the distance increase, the nucleus cannot hold them that tight, so they move around faster. No, they are not, because they are hold on tightly to the nucleus. The shell, yes, the shell has higher energy and the electrons can move around faster. Less binding force, that is why they can move around faster. If there is more binding force, they cannot move. It is less binding force, that is why they can move around faster. What?
You're saying less energy closer to the nucleus, that would make sense. You need more force to remove that electron.
Kind of like the average.
That is ionization energy. So there are so many energies we are talking about. Ionization energy is the energy required to remove the electron, right? As you go closer to the nucleus, you need to provide more energy to remove the electron. But what is the energy? The energy of that shell itself.
It's a low energy because it's not moving the electron.
When we looked at the Bohr energy diagram, we said that the shells which are closer to the nucleus is lower in energy. As we move further from the nucleus, the shells have higher energy. Those are two different things. What you are doing is you are trying to connect those two together. That is why it is sounding confusing or contradicting. Here the energy means the attractive force between the nucleus and electron. That's what we are talking about. Okay? The shell energy is orbital energy. Remember that picture, as you move away from the nucleus, energy is increasing. N1 is lower in energy than N is equal to 6. And from the higher energy, somebody jumps to the lower energy. Light is emitted, which we see as spectra, all that, beginning of the chapter. That is a different sort of energy, Jason. I think you missed that part. That is why. Okay? So ionization energy, again, it is the energy to remove an electron. Okay? It's not about the electrons jumping around in their different orbitals. So don't think that there is only one energy in place. There are a lot of things in place which are holding on to, the electrons, how they are holding on around the nucleus. So ionization energy, the trend is they increase as we go up because the electrons are more closer to the nucleus, so you need more energy to pull them apart. Why they are increasing down the period, across the period? In a period, let's say for example the fourth period, you start at the 4s level and then, fourth period will not be a good example. Let's go to third period where the sodium is. You start at the 3s level and as you move further, your atomic number is increasing, right? But the electrons are added only at the third level, 3s and then 3p. The principal energy level is the same, 3, but electrons are added in the same level, but the nucleus is increasing in charge as we increase the atomic number. When we increase the charge of the nucleus can hold on to those electrons more stronger. That is why ionization energy is increasing, because if the nucleus is holding on to the electrons stronger, you cannot remove it easily. You have to provide more energy. Okay? Well, I'll stop right here and we will pick up ionization energy in the next class and proceed. Read the book also, guys. And I guess last class there were a lot of different things discussed. Don't connect that with this. Okay?